Hello everyone, welcome to the channel. So in this video, I'm going to show you the soil moisture estimation using TVDI approach by Landsat 8 Imagery in Google Earth Engine. So now let's get started. First, to estimate the soil moisture content using Landsat 8 Imagery, first we're going to define our region of interest. Next is to acquire the Landsat 8 Imagery filtered with a specific timeline of for our analysis with a low cloud contamination. And within Landsat Imagery, the surface reflectance bands are first calibrated using by applying the scaling factor, followed by the derivation of NDVI, that is Normalized Difference Vegetation Index, to differentiate the vegetated and the bare surface. And next is the land surface temperature from thermal band is calculated using the standard conversion formula. These two parameters, that is NDVI and LST, are critical for estimating the surface energy balance and inferring the soil moisture variability. So next, the imagery is then categorized into two NDVI based land cover classes: the full vegetation cover when NDVI value is greater than 0.3, and the bare land if the NDVI value is between 0 to 0.2. So the corresponding LST values for both the categories are extracted and statistically summarized using the regional minimum and maximum values. So these value represents the temperature condition under wet and dry soil conditions, which are later used in the physically based equation to compute the soil moisture estimate for each pixel. So the soil moisture is calculated using a custom equation involving the NDVI and LST values scaled by the difference in the thermal response between the wet and dry reference condition. So once we calculated our soil moisture, and in the next step, we're going to visualize the time series by generating the time series chart, allowing the users to observe how the soil moisture changes over a 2-year period. So now let me get back to Earth Engine. So in the first step, we have to define our region of interest. So we have to select our study region of our choice. For example, I've selected this particular region of my study region. Let me show you that. So this is my region of interest. So we can able to see from the satellite imagery a lot of agricultural activities being taken place here. So in this study area, so selected this particular as my region of interest. So to create your study area, first we have to navigate to this option called draw rectangle, and next step, navigate your suitable study region. So I have navigated to my study area. So I'm going to draw a polygon here, that is a polygon over the region of interest of my choice. And once you did that, in the top section we have this variable called geometry, and in that we're going to click this option called show generated code. And from here I'm going to copy the latitude and longitude of newly created study area. So I'm going to copy using Ctrl C in my keyboard, and next step, I'm going to paste this value here. So inside this variable called boundary chords, I'm going to paste it here using Ctrl V in my keyboard. So once you pasted your value, so now this particular variable called boundary chords, that is coordinates, going to hold this latitude and longitude of our newly created study area. So the next step, we have to convert this latitude and longitude into a polygon. So to do that, we're going to define another variable called study area equals to earthengine.geometry.polygon, and we're going to refer to this particular variable called boundary chords. So we are referring to this variable. So we can able to see as the result, this particular variable holding latitude and longitude is going to convert into a polygon. And next step, we're going to center this particular layer. So to do that, we're going to define map.center object study area with a suitable zoom level. And the next step, to add this layer, we're going to define map.add layer study area with the default visualization parameter, and we're going to output the layer as study area. And the next step, we have to load and filter the Landsat 8 surface reflectance imagery. So to do that, we're going to define a variable called Landsat collection equals to earthengine.imageCollection Landsat LC08 CO C02 T1 collection to tier 1. So using this code, you can access the Landsat 8 imagery of surface reflectance imagery. And let me show you this particular image. So this is USGS Landsat 8 level 2 collection to tier 1. So the dataset availability is from 2013 to 2025, and the dataset provider is USGS. And using this code, you can access this Landsat 8 surface reflectance imagery. So you can go through this description about this particular dataset. So this dataset contains an atmospherically corrected surface reflectance and land surface temperature derived from the data produced by Landsat 8 OLI and TIRS sensors. These images contain 5 visible and near-infrared bands and 2 short-wave infrared bands processed to orthorectified surface reflectance, and one is a thermal infrared band processed to orthorectified surface temperature. So you can go through the details about this particular dataset. So the next step, we're going to navigate to the band section here. So in the band section, you can able to visualize the resolution of this particular imagery, that is 30 meters. The resolution of this particular imagery is 30 meters. And these are the following bands that is available inside this dataset, starting with SRB1 to SRB7. So these are the following bands that is available in this dataset, starting with SRB1, that is band 1 ultra blue coastal aerosol, and SRB2, which is band 2 blue surface reflectance, and SRB3 is green, and B4 is red reflectance, and B5 is a near infrared, and band 6 and 7 is a short wave infrared. So let me get back to Earth Engine. So next, we're going to filter it based on a study region. So to do that, we're going to define dot filter bound study area. So study area, so this is our study region, and we're going to apply filter it based on our region of interest. That is our study area. So I've given here dot filter bound study area. So the next step, so we're going to filter it based on our time period of our analysis using dot filter date and specifying a period of analysis starting from 2020 January 1 to 2022 December 31st. And the next step, we're going to filter based on our least cloud contamination imagery. So to do that, we're going to define dot filter earth engine dot filter dot less than cloud cover less than 10. So we are filtering the imageries with the cloud cover less than 10%. And the next step, we're going to filter it based on our WRS path and WRS row. So for example, this particular study area which lies in this particular WRS path and WRS row, so there is a WRS path of 39 and a WRS row of 30. So this particular study area falls on in this path and row. And last, to view the metadata property of this particular imagery, we're going to mention print Landsat collection and Landsat 8 metadata. So we're going to run this code here and let us visualize the metadata here. And so here you can able to visualize the console section. Let me turn this off, the study area in red color. And you can able to see here in the console section, we have this image. You're going to click this option. And here we have this particular option called features. And going to click this. So we have total around 23 satellite imageries are available based on our different filters we applied. So for example, I'm going to select this first image here. So you can able to see we have a total of around 19 bands that is available. And I'm going to select the properties here. And you can able to see the metadata property of this particular Landsat 8 imagery. So you can able to visualize the different metadata properties. And we have this UTM zone. So this particular study area falls in the UTM zone of 12. And the WRS path of 39 and WRS row of 30. So likewise, there is a lot of metadata property for this specific imagery. So in the next step, we're going to compute NDVI and LST. So to do that, to compute NDVI and LST for each image, so we're going to define a variable called spectral param, that is spectral parameter equals to Landsat collection dot, and we're going to create a function dot map function img. So the Landsat collection, which refers to our Landsat 8 imagery, they're referring to this particular variable. And inside this loop function, we're going to create a variable called reflectance is equals to image dot select SRB. So we're going to select all the Landsat 8 imagery band using this particular SRB dot star. So it's going to select all the Landsat 8 imagery. And in the next step, we're going to apply the scaling factor, scaling and offset factor. So let me navigate to the USGS imagery here. So you can able to see we have this scaling factor. You have to apply scaling factor and offset factor before proceeding towards our analysis. So we have to apply the scaling factor and offset factor. The scale factor of 2.75 into 10 power minus 5 and the offset factor of minus 0.2. So we have to apply both this scaling and offset factor here. So to do that, first we're going to refer the Landsat 8 imagery, that is img.select srb.star. It's going to select all the Landsat 8 bands, and we're going to apply the scaling factor using dot multiply 0.0000275 and dot add, that is applying the offset factor of minus 0.2. And once we applied it, we are ready to use it for our analysis. And next step, we're going to create another variable called NDVI equals to reflectance dot normalized difference. So reflectance here, which indicates referring to this variable in which we have applied the scaling and offset factor. So after that, we can proceed towards our analysis. For example, we can create NDVI. So for that, we're going to refer this variable reflectance dot normalized difference, and to apply, we have to use this particular formula, that is SRB5 and SRB4. So this is the formula to calculate NDVI, that is Normalized Difference Vegetation Index, SRB5 minus SRB4 divided by SRB5 plus SRB4. So where SRB5 is the near infrared and SRB4 is the red, and NDVI indicates the vegetation density and health. And this going to compute our Normalized Difference Vegetation Index using SRB5 and SRB4. And last, we're going to rename using dot rename NDVI. And the next step, we're going to create another variable called LST equals to image, referring to our Landsat 8 image collection, dot select ST, the beaten ST beaten band, which is the thermal infrared band. So you can able to see here, this is the ST beaten. So the unit is it is in Kelvin, and this is the band and surface temperature, which represents the thermal infrared band. So let me get back to Earth Engine. So once we selected the ST, that is thermal infrared band, using dot select ST band, and we have to apply the scaling and offset factor again here. So that is we have to multiply. So this particular value, that is to convert from Kelvin to Celsius, we are applying this dot multiply 0.00341802 and dot add 147. So to it's going to result, it's going to convert our Kelvin to degree Celsius, and we're going to rename using dot rename LST, that is land surface temperature. And we're going to rename using dot rename LST, that is land surface temperature. And the next step, we're going to return this particular imagery, Earth Engine dot image and dot cat function. So to hold these two bands together, that is NDVI and LST band. And we're going to copy the system properties using dot copy properties. And in the next step, we're going to extract the LST for the vegetated areas and the bare soil. For example, to extract the LST for the vegetated area, we're going to apply the condition, that is when NDVI value is greater than 0.2, and followed by we're going to apply another to extract the LST value for bare soil. We're going to apply the condition when the NDVI is between 0 to 0.2. So we have to apply both the conditions here in order to extract the LST for vegetated areas and the LST for bare soil. So in the first step, we're going to define a variable called LST vegetation equals to the spectral params dot. We're going to apply the map function here. So we're going to create a loop function, and inside it we're going to mention a variable called mask vegetation equals to image, referring to the Landsat 8 imagery. And in that we're going to select this particular band called NDVI using dot select NDVI. And once you selected this NDVI band, we're going to apply the condition here, that is dot GT, which refers to and we're going to apply this function called dot greater than 0.3. So in this way, you can select the NDVI value that is all greater than 3, that is 0.3. So in the next step, we're going to create a variable called LST veg, that is LST vegetation equals to image dot select LST. So once you selected the LST, and next we're going to apply this function called dot update mask. So based on the condition we have previously applied it, we have selected all the NDVI areas where the value was greater than 0.3, and we're going to update using this update mask and referring to this variable mask vegetation. So referring to this particular variable called mask vegetation. So basically it's going to select all the LST areas where the NDVI values were greater than 0.3. So we are applying this particular condition in order to select the LST areas where the vegetation is available from the NDVI image. And next step is we're going to return this LST vegetation dot. We're going to apply the system properties. For example, system time start and other metadata properties. We're going to copy to this particular image that is LST veg. So to do that, we're going to define dot copy properties img and img dot property names. And the next step, we're going to perform the similar. So we're going to extract the LST for the bare soil. Based on the condition, we're going to apply that is NDVI, the value for between 0 to 0.2. So based on the NDVI value. So for that, we're going to create, so to extract this LST for the bare soil, we're going to define a variable called LST bare soil equals to the spectral params, that is spectral parameter. So we're going to create a loop function using dot map function img. Image refers to our Landsat image here. So inside this loop, we're going to create another variable called mask bare. So equals to image dot select NDVI. So we are selecting the NDVI band and we are applying a condition that is dot greater than or equals to 0 and image dot select NDVI dot less than 0.2. So we are applying this condition that is greater than or equals to 0 to 0.2, that is less than 0.2. So once we apply this condition, in the next step we're going to create another variable LST bare equals to image dot select LST. So we are selecting the LST band and we're going to update this particular using dot update mask, and we referring to this particular variable mask bare, that is referring to this particular variable. Basically we are selecting all the LST areas where there is bare soil. So for that we are using this particular condition here. And last we're going to return LST bare with copy properties, that is that's metadata property of this particular image to this particular LST bare image. So for that we're going to define dot copy properties img dot property name function. And the next step we're going to compute the average thermal values. So we are doing this, so we are calculating this LST bare and LST vegetation in order to apply for this particular formula. Let me show you that. So this is the formula that is, this is a key empirical model is derived from the Temperature Vegetation Dryness Index, TVDI, based concept for a similar physical proxy. So using this we can calculate the soil moisture. So the formula involves soil moisture equals to ID plus ST multiplying NDVI minus LST divided by ID minus IW plus ST minus SW multiplying NDVI. So the SM here refers to soil moisture and NDVI refers to the Normalized Difference Vegetation Index, and LST refers to land surface temperature in degrees Celsius, and followed by the ID, which refers to the max LST for bare soil in dry condition, and similarly the IW is equals to the minimum LST for the bare soil in wet condition, and the VD, which represents the max LST for the vegetated area in dry, and VW is the minimum LST for the vegetated area in wet. And last, to calculate the slope of the dry edge, that is ST equals to ID minus VD. So to calculate the ST value, that is slope of dry edge, we have to ID minus VD. So the ID and VD is given here, the max LST for bare soil and max LST for the vegetated area, and similarly the SW, which represents the slope of the wet edge. So the formula here is equals to the slope of the wet edge, that is SW, is equals to IW minus VW. So the IW is given here, the minimum LST for bare soil, and the VW is given here, the minimum LST for the vegetated area in wet. So based on this formula, we're going to calculate the soil moisture using our Landsat 8 imagery. And this is the formula to calculate the soil moisture. So let me get back to Earth Engine. So now to compute the average thermal values. Starting with the LST vegetation. So first we're going to compute the LST vegetation minimum, and next LST vegetation maximum, and next is the LST bare soil minimum, and next is the LST bare soil maximum. So to compute the LST vegetation minimum, we're going to define a variable called minimum vegetation equals to earth engine dot number LST vegetation. So LST vegetation referring to this particular variable here we have previously mentioned in order to extract the LST over the vegetated areas. and we are referring to this particular variable, and we are applying dot minimum function, and inside we're going to mention dot reduce region, and inside this we're going to mention we're going to apply some statistical function, that is a simple statistical function, that is earth engine dot reducer dot mean function, in order to acquire the minimum thermal values over the vegetated areas, LST vegetation. So we have mentioned earth engine dot reducer dot mean, and the geometry here is refers to our study area, and the spatial resolution. So the spatial resolution for the thermal bands is around 100 meters. So scale we're going to mention as 100. And next step we're going to apply this dot value function and dot get 0. So to acquire in number, so to acquire this in the number, we're going to mention dot value function, and we're going to apply this particular function to get the first value out of it. So for that we're going to mention the dot get 0, so in order to get the first value out of it, and followed by we have to calculate the maximum vegetation. So that is so max vegetation. For that we're going to mention the variable max vegetation equals to, so earth engine dot number and LST vegetation, we are referring to the similar variable. And now we can apply the function dot max function and dot reduce region, and inside the loop we're going to mention the reducer, that is earth engine dot reducer dot max function. So again we are applying another statistical function called max function, so in order to acquire the maximum average thermal value. So for that we're going to mention this dot max function, and the geometry, it is our study region, and the scale is the resolution of this thermal band, which is 100 meter. And similarly, to get in the numbers, we are applying dot values, and to get the first value we're going to mention dot get 0. And similarly, to get the minimum bare, we're going to mention the variable minimum bare, that is minimum thermal values for the bare areas. We're going to mention the variable minimum bare equals to earth engine dot number LST bare soil and dot minimum function and dot reduce region. And similar steps to acquire the minimum the LST, the thermal values for LST bare soil, we're going to mention earth engine dot reducer dot mean function, and the study area is geometry, that is our study area, and the spatial resolution is 100 meter. And similarly, to acquire the maximum bare, the maximum thermal values over the bare soil, we're going to mention the variable max bare equals to earth engine dot number LST bare soil dot max function and dot reduce region. We're going to mention a similar statistical, that is earth function, that is earth engine dot reducer dot max function, and the geometry we're going to mention the study area, and the scale is 100 meters. And to get in the numbers, we're going to mention dot value function, and to get the first value we're going to mention get 0. And the next step we're going to calculate the soil moisture using NDVI and LST. So to calculate the soil moisture using NDVI and LST, let me show you the formula here. So now we're going to calculate the slope of the dry edge and the slope of the wet edge. So to calculate the slope of the dry edge, that is ST, so to calculate the formula is ID minus VD. So the ID represents the max LST for the bare soil, and the VD, which refers to the max LST for the vegetated areas. So in order to calculate the slope of the dry cell. And similarly, to calculate the slope of the wet edge, we're going to make, that is SW is equals to IW minus VW. So IW here refers to the minimum LST for the bare soil, and followed by the VW is minimum LST for the vegetated areas wet. So to calculate the slope of the wet edge. So let me get back to earth engine. So to calculate the slope of the dry edge, so we're going to mention the variable thermal slope dry equals to the max bare dot subtract the max vegetation. So referring to this particular variable, so max bare refers to this variable, and followed by the max vegetation referring to this particular variable. So in order to calculate the slope to calculate the slope of the dry edge, so which is equals to max bare minus that is dot subtract max vegetation in order to calculate the slope of the dry edge. And followed by, to calculate the slope of the wet edge, we're going to define another variable called thermal slope wet equals to minimum bare dot subtract minimum vegetation. So this is going to result as the slope of the wet edge. So now once we did that, we have this both slope of the dry edge as well as the slope of the wet edge. So the next step, we're going to calculate the soil moisture. So to do that, let me show you the formula here. So the formula to calculate the soil moisture is ID plus ST multiplying NDVI minus LST divided by ID minus IW plus ST minus SW multiplying NDVI. So this formula is used to calculate the soil moisture. So let me get back to Earth Engine. So to calculate the soil moisture, we're going to define a variable called the soil moisture series equals to the spectral params. So the spectral param here refers to a Landsat 8 image collection. So in that we're going to create a loop function dot map function img. So inside the loop we're going to create a variable called sm, that is soil moisture equals to image dot expression. So we're going to apply the formula. So we're going to apply this particular formula here, that is this particular formula. That is ID plus ST multiplying NDVI minus LST divided by ID minus IW plus bracket of CST minus SW multiplying NDVI. So this formula is going to result as the soil moisture. So the ID, which refers to the max bare, and ST represents the thermal slope dry, and NDVI represents the image.select NDVI, and LST refers to image.select LST, refers to LST, and IW is minimum bare, and SW is thermal slope vect. And last we're going to rename as soil moisture, and we're going to return SM, that is soil moisture dot copy property. So it's going to copy the metadata properties to this particular image. So once you applied it, next step we're going to plot the soil moisture time series over this particular study area. So for this specific study region, I'm going to turn this off so you can be able to visualize it. So to create a time series analysis for this particular area, we're going to create print ui.chart.image chart series, the soil moisture series referring to this particular variable, and study area, that is our region of interest. And in order to acquire a mean soil moisture value, so we're going to use the statistical function, that is earthengine.reducer.mean function, and the spatial resolution I'm going to mention is as 100 meters, and system time start. And the next step we're going to mention dot set chart type. So we're going to visualize this particular in the line chart, and you can set additional options to this particular chart using dot set options. And the title I'm going to mention this time series of the estimated soil moisture, and the v-axis the title is soil moisture index, and the h-axis the title is date, and the line width is 2 and the point size is 4, and the color of this graph we're going to mention in this color. So this color code, so this particular color code is going to represent the blue color, that is slash ash 1F77B4. so it's going to represent a blue color. So now let us visualize the result. We're going to run this code here. So in the console section, you can able to visualize we have a time series chart here. So starting from so you can able to visualize the soil moisture index from 2020 to 2020. So this graph here represents the time series of estimated soil moisture for this specific study region. So you can able to see this particular areas. So a lot of agricultural activities are taking place here. So you can able to see here from this imagery. And this particular axis represents the soil moisture index, and this particular axis which indicates the year. And let us visualize this particular graph here. So you can able to see here. So the analysis period starts from 2020 to 2022, and the soil moisture variation you can able to clearly observe here. So during the high soil moisture is observed during the month of March till February, March, April, and May, and there is a drastic reduce in the soil moisture during. So there is a drastic drop in the soil moisture during in the month of June 2021. So you can able to observe, and again the soil moisture increases during the month of November, and similarly, so it gets reduced in the month of August. In the August, you can observe the soil moisture has reduced. And similarly the moisture value increases during in the month of December. So you can able to see the rise and fall of the soil moisture value during the selected period of the year. For example, during the June, the soil moisture falls in the study area, and during the month of March it gets raised, and during the month of June it falls, And similarly, during the month of November, the soil moisture increases again. And similarly, and during the month of August, it falls. And during the month of December, it increases. So you can able to observe the soil moisture variation for this specific study region. So let me get back to Earth Engine. So now let us take a look at the soil moisture. So the soil moisture value of less than 0.1, so which indicates very dry, which indicates a high drought risk, and followed by the soil moisture is ranging from 0.1 to 0.2. So the interpretation is dry to moderate dry. So the stress begins for the sensitive crops and irrigation is recommended, and followed by the if a soil moisture ranges from 0.2 to 0.4, it is moderate moisture, suitable for the most crop and ideal range for the root uptake. And last, if a value ranges from 0.4 to 0.6, it is moist to wet, so optimal for crop growth, no irrigation needed. And followed by, if the soil moisture ranges from 0.6 to 0.8, it is very moisture and near field capacity, may leads to waterlogging for some crops. And if the value is greater than 0.8, it indicates saturated and possible waterlogging, no more water can infiltrate. So let me get back to Earth Engine. So in the next step, I'm going to apply the land cover mask to exclude the water and barren land cover types. So for that, we're going to use this particular dataset, that is Dynamic World V1. So the dataset availability is from 2015 to 2025, and the dataset provided is World Resource Institute Google. And using this script, you can access this particular land cover dataset, and the resolution of this particular data is 10 meters. And these are the following land cover types that is available in this dataset, starting with water, tree, grass, flooded vegetation, crops, and bare snow and ice, and build up areas. And label class table is given here. So this set of colors which indicates this set of land cover classes, and the values represented here for each land cover classes. So water will be represented as a 0, and the bare will be represented as 7. So let me get back to Earth Engine. So now to apply the land cover mask and to exclude the water and barren land cover types. So to do that, we're going to define a variable dynamic LC equals to Earth Engine.image collection Google Dynamic World V1, and in that we're going to select this particular band called label. So we're going to mention dot select label, and we're going to apply the filter function based on region of interest. So for that, we're going to mention dot filter bound study area, and last we're going to apply the dot mode function in order to acquire the most common land cover types. So for that, we're going to mention as dot mode function. And in the next step, we're going to define another variable called landmask equals to the dynamic LC, which represents this particular variable, that is our dynamic land cover dataset. And I'm going to mention dot not equals to 0. So 0, which indicates water, and the dynamic LC, that is LC, is dot not equals to 6. So the 6 here represents the barren. So basically, we are excluding these two set of classes here, water and barren, and followed by we're going to add this layer map.add layer landmask.clip based on our study area with the default visualization parameter. We're going to output the layer as valid land cover mask. So now let us take a look at this. So in the layer, if we have this layer called valid land cover mask, so you can able to see here the dark patches which indicates the water, and the barren land cover classes being masked. So in the next step, we're going to stack the soil moisture image and apply a mask. So to apply so we're going to apply this particular mask in our soil moisture image. So to do that, we're going to define, that is excluding the water and barren. To apply it in our soil moisture image, we're going to define another variable called sm composite equals to soil moisture series dot 2 bands. So 2 band function we are used to stack the bands. So for that we are using dot 2 bands, and to update this to exclude the water and barren, we are mentioning dot update mask land mask, referring to this particular variable where we are excluding the water and barren land cover types. And next step, to add this layer, we're gonna mention map.add layer sm composite dot clip based on our region of interest, and with the default visualization parameter, and we're gonna output the layer as soil moisture composite. So now let us take a look at this particular imagery. So we're gonna navigate to the layer section, and I'm gonna turn on soil moisture composite. So this is the soil moisture composite of the study area. So now in the layer section, we're gonna navigate our soil moisture composite image. So in that, we're gonna click this option, and now you can able to see we're gonna select to single band grayscale, and you can select your soil moisture according to the date. So for example, I'm gonna select this particular one, and I'm gonna apply stretch 90%, and it's loading here. So now here you can able to observe here the soil moisture value ranges from 0.07 to 0.4. So from the table, you can able to see from 0.4 to 0.4 to 0.6, it is moisture to wet, it is optimal for crop growth, and no irrigation is needed. So let me get back to Earth Engine, and I'm gonna click apply, and now let us visualize the result in the grayscale. And I'm gonna turn off this other layer, that is land cover layer. So now here the image got loaded up here. I'm gonna turn to a satellite mode here. So from this image, you can able to observe here. So all the white areas which indicates the high moisture values, and all the darker areas which indicates the low moisture value. So you can able to see here all this this study area has a higher moisture value compared towards the outer side here. So it has a lower moisture content. So you can able to see from this image here, and this is how we can calculate the soil moisture value here. So in the next step, we're going to export the soil moisture image to our Google Drive. So to do that, we're going to mention export soil moisture, that is to export the soil moisture image to our Google Drive, we're going to mention export.image to drive, and the image I'm going to mention sm composite.clip study area, referring to our region of interest, and we're going to clip it based on our study area, and we're going to apply this float function. And in the next step, I'm going to mention as the description is soil moisture map, and the folder is soil moisture export, and the spatial resolution is around 30 meters, and the region is the study area, and coordinate reference system is EPSG 4326, and the max pixel value is 1:10^13. So now we're going to navigate to the task section here, and I'm going to click this option called run, and now a window pop up saying initiate image export, and we have the scale is 30 meters. We're going to export to our drive, and drive folder is soil moisture export, and the file format is in GeoTIFF. So now to export this image to your Google Drive, so you have to click this option called run. So next we have to take a look at the application part of this analysis. So the application, so the agricultural monitoring and crop management. So the soil moisture is critical for crop health and yield, and helps farmer and the planners so assess the dry versus the moisture zone to optimize the irrigation scheduling and crop selection, drought preparedness, and support precision agriculture by detecting the water stress in crop zones, and groundwater recharge and hydrological studies, and to used to identify the zones of low soil moisture which may impact the groundwater recharge potential, water balance analysis, and integrated with the models like SWOT or mudflow for input calibrations. And the third application is the drought monitoring and early warning. So helps track the temporal soil moisture trend from 2020 to 2022, can be used to detect the early onset of agricultural drought, and inform the drought severity classification, and guide policy decision in water scarce region. So now let me get back to Earth Engine. So in this video I have shown you soil moisture estimation using a TVDI approach by Landsat 8 Imagery in Google Earth Engine. So thanks for watching, and make sure that you subscribe to our channel and give us a like, and the code link will be given in the description of this video. So thanks for watching.